get all
Okay. Yeah. Just because both concepts from these I really just Spectral Network and Fukaya categories with predications already.
Okay, thanks very much. So thanks very much to the organizers. I don't know if they're in here yet, but anyway, it's a great pleasure to come to the meeting in Miami for many times now. Also a great pleasure to dedicate this to Kenji Fukaya. So we'll be talking about Fukaya categories here. So the basic topic is stability conditions and spectral networks. So this is joint work with Fabian Haydn, Lumil, and Pranav. And so this is a project on the conjectural correspondence between stability conditions, let's say special Lagrangian and stability conditions. So this is I mean, mostly due to Maxime, if I understand. I think Jan, I guess, also. It's supposed to be closely related to the wall crossing question. I don't think we are able to see that all that clearly at this point, but in the future it will definitely be closely related to the wall crossing picture. And is a generalization of Bridgeland and Smith. And in some sense, guided. So there's a paper by Fabien Lumil and Maxime, which reproved Bridgeland Smith result using so I think what we're doing in this project is kind of based on that kind of idea. So the basic idea is that special Lagrangians are supposed to be viewed as the same thing as spectral networks. So to make this correspondence, so the spectral networks are certain graphs inside the complex plane, and they have trigonal or other vertices, trigonal basically. And how do you view those as special Lagrangians? So the idea is to look at the notion of Fukaya category with coefficients. So I guess this could be probably defined over any symplectic manifold. I personally only understand that if I understand anything at all, it's only in dimension 2. So that's what I'll be doing here. So let's let X be a Riemann surface. But you guys, if you want, can replace that with a bigger symplectic manifold. But now what's the idea? The idea is to have a sheaf of categories D over X. And so a little bit more precisely, this is what Karpanov and Checkman called perverse Schober. we sort of take the star of Karpanov in the collaboration diagram. So there's Karpanov with Shechtman. And Diekerhoff. So the idea of perverse server we're not really going to meet today in the sense that that would be the case where the sheaf of categories has some singular points. And at the singular points, the notion of perverse sheaf of categories is to have what's called a spherical functor at the singular points. We're not going to have that today. For us, D is just going to be constant, so you don't need to worry about that. But there's the notion of a section of, so if we have a graph, then we can define we get a category gamma of G comma D of sections of D with over the graph G. That's from the paper by Karpanov and Diekerhoff. So let me just explain that briefly. So the idea is to draw a picture like this. So let's assume that our graph has trivalent vertices. When you have a graph with higher valency vertices, the idea is to resolve it into a bunch of trivalent vertices. And part of the statement, this is like proven in their paper, I think, is that the answer doesn't depend on how you make that deformation. But the idea is, so if we have a graph that looks like this, so our Riemann surface is just going to be a flat plane, and in fact, for us, X is going to just be the complex plane. So that's just our whiteboard here. So if we have a graph, and we want to know what it means to have a section of the sheaf of categories over the graph. So D is a triangulated categories. So let's say constant. Since it's constant, you don't really need to call it a sheaf, but the idea is that ulteriorly speaking, that would have some, maybe you could have some monodromy and stuff like that. But for today, D is just a constant sheaf, so to speak, of categories. But I've triangulated like DG, pre-triangulated categories. And now what does it mean to have a section? So to have a section, it means that we're going to have, on each of the edges, we're going to have like A1, A2, A3. So AI will be objects of D. But now what happens at the trivalent vertex? So the idea is to make an exact triangle. So something like A1 into A2 into A3. Okay. So that's the idea of having a sheaf, of having a section. So it doesn't really mean a section in the classical sense. It means a section, but with the idea that at the trivalent vertices, we're supposed to have an exact triangle. Okay. So now what about spectral networks? So spectral networks were introduced by Gayoto Morovnitsky. For some physics motivation, which I'm sure is actually closely related to what we're doing here, but which I wouldn't be able to understand. So we're just going to look at spectral networks. Again, we're just going to be in a completely simplified situation. So we're going to look at spectral networks for the spectral cover. So let's just take an extremely simple case. P cubed equals dz cubed. So that's an equation. This defines a spectral cover, sigma inside the cotangent bundle of X. In our case, sigma is just the union of three sections.
The real spectral cover is just something which is embedded in the cotangent bundle.
A spectral cover is anything is a curve embedded in the cotangent bundle, which is finite over x. In our case, it's going to be better than finite over x. It's just 3 copies of x sitting at the point dz j times dz and j squared times dz, or j are the cube roots of unity. But I mean, in general, spectral covering is going to have an equation of the form, and then we can write this p cubed minus dz cubed equals 0. So p is the momentum coordinate, so that p means the coordinate in the cotangent direction. So in general, there's going to be some equation of some degree, and that degree is the degree of the spectral covering. Here we're just taking the simplest possible equation. It's just that p is just the cube root of dz cubed, so there's just 3 possible differentials. And now what do? So you take, so if we take lambda I sections of sigma, then lambda I minus lambda j, let's call that lambda ij, these are differentials. Of course, in this oversimplified situation, there's a lot of the picture which is interesting, which is not being seen here. For example, in general, sigma will have some ramifications, so these lambda i's are going to interchange. So these are not really well defined, they're kind of locally well defined. In our case, they're just constant. And then the real part of lambda ij, this defines affiliation. Now, what's a spectral network? So a spectral network is just a graph such that the edges are labeled by pairs ij, and an ij edge goes along the real part of ij foliation. So in our case, the picture is kind of easy because there's only there's 3 different pairs ij. There's 3 different differential forms. These 3 different differential forms are just they just define foliations that are, maybe I'm not drawing this correctly, but 60 degrees apart. Okay? So we just have foliation, we just have a constant foliation by lines on the complex plane that are 60 degrees apart. So, but in the general theory, that comes from this. The lambda i's, these are one of these 3 differentials. We take lambda I minus lambda j, but again, those are all, there's just 3 multiples, and there are still multiples of each other by the cube roots of unity. Then we take the real part of those. The real part of those on the complex plane, that just means that you turn, when you multiply by the root of unity, you're turning by 60 degrees, sorry, 120 degrees. So that the picture looks like that. So a spectral network means that your edges are allowed to just be any of these 3 slopes. So there's only 3 possible slopes of the edges. And of course, if you want to have an interesting graph, you're automatically going to have some trivalent vertices. Now the rule of the trivalent vertex is that you have like ij, j, k, I, k. So just from the foliations, at a trivalent vertex, the indices have to behave like that. Now how do we view that in sort of Fukaya category types of terms? So the idea is to look at the category D is the category A2.
Right, so it's representations of just a quiver.
Like that. And are labeled. So D2 is the representations of the A2 quiver, but it's actually more invariantly thought of as the Fukaya category, Fukaya's idol, I guess, of the plane with 3 points in it. These 3 points are really the 3 points in this plane is really the cotangent fiber, and the 3 points are the 3 intersections with the spectral curve. So there's basically three kinds of objects. There's going to be, and so let's just label these like I, J, and K. So in the Fukaya-Seidel category, we're going to have Lagrangians like that, and like that. But the point is that the Lagrangian, the JK, sorry, maybe the IK Lagrangian is an extension of the IJ and the JK one. So we have like, I'm not sure which direction the maps go here, but. We have an exact triangle in this A2 category, in D, which is. So what that means, so this is kind of the fundamental observation, which allows you to transform the picture of spectral networks into a picture of some type of Fukaya category, which is that this labeling that happens in Gayato Moronitsky's papers by IJ, JK, and IK, you can actually think of that as being labeling by objects in the fiber category. And the fiber category is itself thought of as a Fukaya category or something. Now, kind of roughly speaking, this whole the idea of this project, this was explained by Maxime in his String Math 2016 talk, which might still be on video. Unfortunately, he didn't write a paper in the proceedings about that, which would have been good, but anyway. So the idea is that if you have a fibration of symplectic manifolds, then you can sort of stretch or shrink the symplectic form on the fiber. And in our case, the fibration is the cotangent bundle of X mapping to X. Then you can try to look at Lagrangians in some kind of limiting case where, now I forget if it becomes large or small, but the fiber becomes, maybe let's say small, okay? So in the limiting case where the fiber becomes small, then you can look at Lagrangians, and in the limiting case, Lagrangians start to look like a Lagrangian in the base and a Lagrangian in the fiber. That's of course not true in general. I mean, in general, Lagrangian in a product is going to be something strange. It's not going to just decompose as a Lagrangian in the base, and then over the Lagrangian in the base, Lagrangian in the fiber. The idea is that in the limiting situation, that is actually supposed to happen. And so these spectral networks that are labeled like that, we can think of them as actually sort of limiting Lagrangians for this fibration. So in other words, over each edge, we put, like over the IK edge, we put the IK segment in the fiber. And then at this point, well, we're going to get an exact triangle. And actually, you can actually try to draw that. You can, I wasn't too good at that, but we were discussing that with Andy Knightsky, trying to draw on the blackboard what the Lagrangian looks like sort of just before you hit the limit point. And you can actually sort of try to draw that. I mean, I'm sure you guys can do that much better. Because of course, the problem is that you have to fill in this triangle somehow or other at this point. So at this point, this triangle gets filled in at the same time as the Lagrangian sort of curves like that. So there's some picture you can make where as you go towards this point, the Lagrangian sort of spreads out a teeny bit, and it sort of at the same time it fills in this triangle. But sort of at a general point of one of these edges, the Lagrangian in the fiber is just going to be the like JK, just that edge in the fiber. Okay? So that's this idea of looking at sort of a relative notion of Fukaya category. So what do we do in technical terms? So we'd like to define Fukaya category a Fukaya category of X with coefficients in D, basically. So D is, I mean, in a general situation, D is going to be this chief of categories, and X is going to be our complexity base manifold. And that's supposed to be something like some limiting Fukaya category of the fibration, if D is thought of as the Fukaya categories of the fibers, the fibration. Well, okay, but this is good news for me, because this reduces this higher dimensional pictures, which is complicated and difficult to understand, into pictures that you can just draw on a surface. You can just draw the pictures like this, okay? But then we just have to remember that over the edges of the graph, you're supposed to put an object of the category D. Okay, so, roughly speaking, objects are Lagrangians in X, which is to be thought of as graphs, with edges decorated by objects of D. Then plus this triangle condition at the vertices.
Structure, not condition.
Sorry?
Structure, not condition.
What's the structure?
No, the second vertices, there are also some other triangle, right?
That's the structure, yeah. So that's right.
You take traveling graphs or?
Well, if it wasn't a trivalent graph, then you would first resolve
Yeah.
into trivalent graphs and then put that condition. Or I mean, so what Fabian would say is that in general, if you have an n-valent vertex, you're supposed to have a representation of the AN
Yes, so just
category.
AN instead of A2.
Yeah, basically. Because exact triangles can also be thought of themselves as representations of A2, which we kind of saw here roughly.
For example, if the spectral cover will be more than 3, they probably need more than I will.
In the special Lagrangians? No, in general, you'll still just have this type of situation. This is what Gautam-Marinsky call a collision. So for a kind of a generic choice of everything, you expect, I think, to only have collision. So that's the general type of thing. So what are we actually doing? So we're actually looking at the following case. Sorry. I need to say one more thing about the general condition. One more thing about the general setup is that, now we want to talk about stability conditions. So stability, so we assume given a family of stability conditions, on D with coefficients in the T star of X. In other words, the central charge from D at a point X, instead of mapping into the complex plane, it's going to map into T star X. I'm not sure about the star here, I have to say. Either TX or T star X. Maybe not. This is isomorphic to the complex plane. But in general, there's a rotational aspect to that. So this is isomorphic to the complex plane, but not with a canonical choice of basis vector. And so this structure, if you had like a Riemann surface, a compact non-trivial Riemann surface, this would be a different structure than just a stability condition. In our case, of course, it's the same because in our case, X, I guess I erased that. That was there. X equals C, so this is just canonically equal to C. So for us, it's just a single stability condition on the fiber category, which is A2, and it's thought of as given by this description of A2 as being the Fukaya-Seidel category of the plane with respect to 3 points. So what I've drawn here are actually themselves the stable objects, or the spectral Lagrangian. And then you would like to say, so then the conjecture, I guess, if I'm not botching this up too badly. the conjecture is going to be, so I think this is just a part of Maxim's conjecture that he was talking about before, about special Lagrangians, but it's kind of it's the limiting, it's the version of of that conjecture for this limiting picture where you shrink the fiber of a symplectic vibration. The conjecture is that the F, this Fukaya category, fxd, will have a stability condition such that the stable objects have spectral network representatives.
And the graphs are straight, the lines are straight.
The lines are straight because, I mean, they're straight in the sense of this stability condition on the fiber. So an edge is supposed to be decorated with an object. So the spectral network is that object is supposed to be stable of a certain slope. And the edge, I mean, the total slope is the slope of the edge, maybe minus the slope of the, I mean, maybe the slope of the object in the fiber minus the slope of the edge or something like that. So on an edge, E, you have an object, A of E, that should be stable of phase phi of A of E. So the stable objects of phase theta are going to have spectral network representatives where on an edge E you have an object A of E that has phase phi of A of E, and theta is equal to something like phi of A of E minus the angle of the edge. And the point is, I'm not sure about the signs here, but that's supposed to be well defined given the fact that the central charge goes into the something which is the tangent or cotangent bundle. And that forces the edges to be straight because I mean, along its given edge, it's always the same object. So it's straight in the sense that it's straight in terms of the foliation that you get. This condition here, roughly speaking, corresponds to giving you the spectral curve. And then that's going to be straight along the foliation given by exactly in this way of the spectral curve. So now, what are we doing here? Well, we were trying to prove the conjecture in general. That was a first phase. Then we said, okay, let's just do an example. That was another phase. So our first version of an example was, okay, let's just consider the fiber category A2. Then we reduced the example a little more. Okay, let's consider the fiber category A2, but where it's just constant and the stability, the spectral network is constant, so the stability condition is constant. Then that we also didn't succeed there. So now we've gotten down to a really special example. So what we're doing. What we're doing is the case, so the case, which we call this A5 tensor A2. So X is the complex plane with respect to 6 points, with 6 marked points. The TIs are vertices of a regular hexagon. D is constant, always equal to A2, and the stability condition the constant stability condition so that the object Ij has phase, say, dz or something like that. JK, J. something like this, I mean, the statement here, the 3 point, this is just going to correspond to this spectral curve. So now in this case, well, in general, f of x, comma, d is going to be just a5 tensor d, which in our case is a5 tensor a2. So, because the Fukaya cycle of x is just a5. So one way of seeing that is so we have so x is, x is c with 6 points. So that's like here x is c with 3 points, and the category is a2. So it's always, the number that goes here is 1 less than the number that goes here. The way of seeing that is by taking cuts. So if we take these 6 points, if we have some kind of Lagrangian, or something like that. So I can use my color thing here. So we can make the following cuts. So this gives us 5 objects. So if we take our Lagrangian and cut it along these 5 curves, then intersect the Lagrangian with these 5 curves, 5 sort of testing curves, then we're going to get 5 objects which are the cut of the Lagrangian with respect to these testing curves. And then there's going to be maps from one to the next one. So there's going to be 4 maps between 5 objects. So that's the A5 thing. And then if we take Lagrangians with coefficients in a fiber category, that's just going to be the same thing, but where these objects are objects of the fiber category. So the explicit description of the Fukaya category is just it's the category of sequences of 5 objects of D with 4 maps between them. And that, I guess, is called A5 tensor A2.
Sorry, Carlos, I think there's confusion. Because for spectral networks, we put the fiber cable not literally n cable, but collateral to double. And
Yeah, well.
And now if it's not double, it will be something in complex surface.
Well, we were saying that we were using that terminology for quite some time. Fabian, I think, convinced us that it's going to just be easier to talk about the A2 without the double.
Yes, it will be a special class of spectral network that will kind of oriented, not arbitrary spectral network, because if you want to be, it will be special class of spectral networks.
Are you saying that there's a direction in that case?
Yeah, there's some direction.
Oh, maybe we need to think about that question. Yeah, okay. I'm not sure. We'll think about that. Thank you.
Definition you get for the network includes
Yeah, you get more
the
like-
direction, right?
And in this case, you get more like honeycomb pictures, and in general, for general things seem to go outside down.
Are you sure about that?
Yes,
Well, okay, we'll have to think about that. But that's true. But so the thing that Maxime is saying is where you take the spectral curve sigma, then you over the spectral curve sigma, you take a conic bundle
Yeah.
that's branched along the spectral curve, and then you look at actually sort of compact Lagrangians inside that thing.
It's one story, yeah.
That's the 3-dimensional one.
Yeah. And do it's more like
What we're doing here is just in the 2-dimensional thing.
C.
Yeah. Well, let me say, I'm not sure exactly what to say there, so let's just continue here. Okay, so this is the Fukaya category. But I mean, we can do this really for any fiber category D, but then there's going to be a question about what does the stability condition on D look like. So I think the only thing we're really using is the fact that D has a stability condition with really only 3 possible phases. So anyway, let's see, what am I saying? So this is the Fukaya category. That's why we're calling this case example A5 tensor A2. Now, what is a spectral network? So in the spectral network, it means that we have to have edges that look like that. And these edges have to be decorated. So let's maybe change notation here. So the 3 basic objects, so the 3 objects of our D, which is A2, are called A, B, and C. And sorry for those of you in the back, but let me write down the exact triangle. There's an exact triangle A, B, C. And the faces are 0, pi over 3, 2 pi over 3. So this fits in nicely with this exact sequence. So we have a phase 0, a phase pi over 3, a phase 2 pi over 3. The phase here is 0 plus pi. So in this exact triangle, all these maps, they're all kind of the same. They're all maps going from a stable object to a stable object of phase pi over 3 bigger. Okay? So now a spectral network is just going to be a graph, whatever, where the edges are labeled by like A, B, C, A, B, C, B, and so on. So there is a, I mean, the labeling of the objects has, I mean, we're not in the Z2 graded here, we're in the Z graded category. So D is a Z graded category. So that means that you need to be a little bit careful about lifting the direction of an edge in the unit circle bundle of the complex plane, lifting it into the universal cover of the universal circle bundle. So you need to sort of determine the direction of the edge. Somewhere there. That's why you see maps from A to B to C to A, it looks like. So this map is going to be from C to A1, basically. So in spectral networks, it's just going to, anything that looks like that, any graph that looks like that in our complex plane is going to be a spectral network. So the edges have to be off by 60 degrees, and the labeling has to sort of correspond like that. And at that point, you're going to get it. This is going to give you a special Lagrangian object of phase equal to the angle of the whole picture plus the phase of any one of these objects.
So when you drew that picture, it looks like you somehow chose at some point to make 2 of those vertices, the maps are going clockwise, and the other one is going counterclockwise.
I know, it always goes from A to B, it always goes A to B to C.
So that was, so when you labeled those edges was when you made the choice of which way your vertices went.
Yeah, there has to be a global choice made, which I definitely can not guarantee you that I'm doing this in any correct way, but there has to be a global choice of the orientation direction inside the surface and the orientation direction inside D and so on. I mean, there's choice made there now. There's a convention, there's lots of conventions, I mean, I'm sure you guys know all about this, of Maslov indices and stuff like that, which I don't know very much about, but I'm learning. There's conventions that say that that at a triangle, the maps are going to go in one direction, but not in the other direction. Okay. And that triangle is supposed to be the triangle that's this triangle. And the phases are supposed to work out so that, and that's why this plus or minus here, I mean, what formula you have to put there kind of depends on how you choose your conventions here. So, but these are all supposed to have the same total phase. Okay. That's the point. But that's a good question. So the point is that this formula here and this exact triangle thing, and the fact that at a vertex you have a triangle, those are all supposed to work together to make it so that miraculously in the spectral network picture, you get an object where the total phase is always the same. Okay? That's the idea of having a special Lagrangian representative. Okay, so how are you? Okay. So let me just now say, what can we do is we don't actually have a proof of anything. but we can sort of explain some things. So I'd really like to explain two things. One is how to define stuff. And two is pictures. And maybe three, like towards the sketch. So towards the sketch to prove of the conjecture in this case, which you'll see that we're really cheating quite a bit. I mean, even if the proof actually is given correctly, it's still sort of cheating in some sense. But so let me just start by the pictures, because those are sort of fun. That's a little bit of a break. So the pictures. So this was, I think, after last year's conference. This is, of course, updating, continually updating the status of the report on the project. So I think that I've said most of this already last year. But I think the pictures, we figured that out after the conference last year. So this, I guess, will be new, unless you see it somewhere else. So what are the pictures? So this is the picture of the standard phase. Okay. So the standard phase, I'm going to just pick a phase to call that the standard phase. So we're given our 6 points, which are the vertices of a regular hexagon. Okay. Now we can choose the phase of the object that we're going to draw. Okay. So the goal here is to fit a spectral network into this picture. There's one totally obvious way of fitting a spectral network into this picture, which is to just draw a 6-fold point. Okay. So this is the spectral network, so we're going to put like A here, B here, C here. So think of this as two of those collisions superimposed. Okay. But so this is actually a slightly complicated point of the picture, because there's two different ways of seeing this picture. One of them is to think of it as just a direct sum of two different collisions like that. The other way is to think of it as just a direct sum of 3 lines. So this is either 2 collisions or 3 lines. Or you could have some extension data. That's a harder thing to understand. Now let's continue with this. So can we do any other kind of spectral networks? So Fabian tells us that for some general reasons, which I don't know about, but many of you in the room do know about, for some general reasons, we expect to have a one-dimensional parameter, a one-parameter family of pictures. So let's just draw a one-parameter family of pictures. So how can we draw a one-parameter family of pictures? Well, we can just draw a hexagon inside here. I don't know how well I'm drawing this. My edges are supposed to all have, the good slopes. So if we draw a one-parameter family of pictures, now let's label this the same way. This is A. So that's going to be B. That's going to be A again. That's going to be C. No, that's right. That's B. B. C. Okay. So the point is that this vertex here can sort of expand out and grow into a hexagon. Okay, that's a perfectly good spectral network. Now the bounding cochain elements are going to create kind of a monodromy parameter around there and so on. And then this hexagon can sort of expand out, and then there's a third way of drawing a picture, which is just to connect the edges like that. Okay. And again, let me not do what you can imagine, exercise on your papers to label these. But so this one is either, this one could be a direct sum of 6 segments, or have extension data. So the moduli space of objects in this picture really looks like this. So the moduli space of objects in this picture looks somewhat like this. So we have this segment, which is the different sizes of a hexagon. At one end of the segment, those hexagons can degenerate into a direct sum of 6 objects. That's kind of at the end, the very end of this squiggly line. It's when it's a direct sum. And in between here, there's some extension data, which gives you a monodromy class, which is going to be in the, it's going to be a power of t in the Novikov ring, basically. And here, you have 2 kind of endpoints that are far away. One of them is the direct sum of 2, and the other is the direct sum of 3. And in both cases, you again have a monodromy class. You sort of have an extension data class, which is which could in principle be some power of t in the Novikov ring. So I gather that this picture sort of fits in as a very basic case of some other conjectural stuff. More general. I mean, kind of, I guess in general, one expects to have sort of a polyhedral decomposition of some kind of space of stable objects, something like that. And so I think, but we really haven't worked at this at all. I think this should actually best be viewed as sort of sitting inside the Berkovich space of the moduli space of stable objects. For a given slope, there's going to be a moduli space of stable objects of that slope. So we're working over the Novikov field, say, which is non-Archimedean. And so it should have a Berkovich space. And this should be a sort of a picture inside the Berkovich space, but there should be actually a segment inside the Berkovich space which corresponds to these pictures where the hexagon sort of has a variable size. So let me just, now the next question for the pictures is how do we get to the stable objects of other phases? So this was the standard phase. So now other phases. So this is kind of cute actually. So the point is that to get to a stable object of another phase, we take a stable object of the standard phase and we start to modify it. Okay? But it's always gonna have inside the picture. So this was kind of the thing which we realized by drawing some pictures. But inside whatever picture of the spectral network you have, inside that picture, there's always going to be one of these pictures. Okay? And so to get to another picture, we start with the sort of the little thing inside, and then we start to modify it. So let me just explain how that works. So let's start with a little thing inside, which is kind of the generic point, which is a hexagon. So we start with a hexagon that has some edges. So that's our little picture. Well, now what can we do with that little picture? We can complete it. So when you do this, you really have no choice but to be drawing stars of David on the blackboard. So you shouldn't be worried about that. So the first thing to do is the first way of extending the picture is to do something like that. Okay? And so again, the labelings the labelings are determined by the slope of the edges, hoping that I'm correctly drawing the slope of the edges, you might say. Okay. So we just keep the same labeling. Then we just add a collision at each one of these points. So it means like this A thing is going to sort of turn into a C and a B. The A can sort of turn into a C and a B, and then they can go out and meet up over here, okay? So you get a coherent labeling. But now if you notice, this is now a picture. So I'm keeping the slope the same, but we've rotated our collection of 6 points, okay? Now our collection of 6 points looks like that. So what that really means, so let's not do this because it's going to be too hard to draw, but what it really means if you wanted to have the original 6 points, then you'd have to take this picture and rotate it back until these 6 points were in the same position as that, okay? Does everybody understand that? that's gonna make the total phase of these edges change, okay? So instead of changing the total phase of the edge, which is difficult to draw because you have to erase it every time, we're just gonna grow this picture and that's gonna change the total slope of our 6 points. But that's the same as changing the slope of the edge. Now at this point, there's a choice. So at the first step, for some reason, there wasn't a choice. But at this point, there's a choice. You can either go to the left or to the right. So let's say go to the left. So. You sort of get a pinwheel. Okay. Well, I didn't draw this. I did this one, so this one's not so good. And again, we get a regular hexagon, but again, the slope is slightly changed. Now you could keep going to the left, to the left, to the left. Keep going to the left, you get really a spider web picture. That was really the first thing you think of. The first thing you think of as to how to fill 6 points like that into a spectral network is you start drawing a spider web, basically. You sort of spiral in from here and get in here and then go back out. So that's going to give the picture that you get by just choosing always going to the left. But instead of doing that, let's go to the right for once, if I can. So let's see, going to the right is going to be not so hard. Not so easy. I think this is correct. Might be messing something up here. But draw something like that. We'll worry about this picture here. These ones are about correct. So at each stage you can go to the left or to the right. You get these hexagons get bigger and bigger. So then you have to turn and shrink them back down into the original picture. And well, if you think about it a little bit, you see that you'll get any kind of rational slope that way. And it's actually a continued fraction expansion of a rational number that tells you whether you go left or how many times you go left and how many times you go right. So it turns out that that's the picture of all the possible spectral networks. So all the possible spectral networks for this picture come from this operation, starting with one of these three types of spectral networks in the middle here. And, okay. So now I promise you how to define stuff. So these are the pictures. So then the goal of the theorem is to prove that these are exactly the stable objects. So that any stable object of this A2 times A5 category has a representative that looks like that. Okay, so now what about definitions?
Does this pictures that you've drawn allow you to draw like a complete picture now of this Berkovich skeleton of the space of stability conditions?
Well, I think the picture is always going to be this thing. So these different pictures that are more and more complicated, those are pictures for different slopes. And the idea is you can get any slope that you want that's going to occur for a reason which I'll say in a minute, by doing one of these pictures. But then within this picture, so maybe I was going to say that but then decided to skip it, but let me say it. Within this picture, there's this choice of segment, which is the size of this interior hexagon. And when you get out to here, well, if you think about it a little bit, when you get out to, say, the outer case, then those 6 segments, they actually generate 6 subspectral networks. So there's a way of filling in a spectral network in here that doesn't look symmetric like that. That's just because it happens to come from one of these edges that sort of devolved into a subspectral network, or one of these collisions in the middle, or one of these 2 straight edges in the middle. If you take a straight edge in the middle and sort of follow it out, you'll get a subspectral network of this thing. And so the point is that it's the same picture at all those different slopes. Let's see, so for the definitions, so we just, if G is a graph, so we have a disk, so our marked points, well there's 6, but suppose we have some marked points. we take any kind of a graph. So these are going to be some complicated graphs. Whatever. So if we have a graph inside the disk with some marked points on the boundary, then we take the dual graph. So the dual graph, we put points in the regions. The regions are labeled by their area. Okay, so there's a real number, which is the area. We take the dual graph. Take a spanning tree. With, say, leaves at the edges. The leaves of the tree should be maybe at the edge of the graph. And then this corresponds to a system of arcs. Okay, so let me just do an example here. Let me do an example with 3 points on the boundary. If you have a graph that looks like that, then your dual graph is going to have 4 vertices. And we can take a spanning tree that might look something like that, for example. And then the system of arcs is going to look like this. So then we take the dual system of arcs. So that's going to go from here to here, from here to here, and from here to here. And now we just take the Fukaya category. So now we take the category of objects over D. So we just take the Fukaya category whose objects are objects of D over the arc. So an object is an arc labeled by an object of D. Okay. And then we add more Cartan elements. Sorry. Before adding more Cartan elements, now we have disk directions. The disk corrections are just, in this case, are just exactly the ones given by, for example, I think Fabian said that they did you guys did that in the Haydn Kaczar-Konzevich, but also I think it's just basically Abu Zaid explain how to do that, maybe Seidel, I mean, just standard. Because these are just smooth Lagrangians. And we're doing a partial wrapping at these vertices, so you sort of partially wrap in a certain direction at the vertices. Okay. Then we take MC elements. Maybe the only slight detail which needs to be said here is that the Morakantai elements that we're looking at, so I don't know how to explain this quickly, but the Morakantai elements are allowed to have coefficients in the t to the alphas with alpha strictly positive in the Novikov ring. And they're also allowed to have t to the 0 coefficients, but a t to the 0 coefficient is not supposed to be an endomorphism of an object on an edge. It's only supposed to be an arrow at the wrapping. So the t to the 0 coefficients only occur at the wrapping. That's actually the thing which allows you to get sections over the graph. If you add this possibility to your Morakantai element, then you get sections over the graph. So let me finish. Good. The green one is not good. Erase here.
Oh, it's perfect.
Sorry about that for the next talk. So what do we get? We're going to get a Fukaya category with coefficients x comma d. So we sort of take a direct limit over the graphs. We're going to get a category defined over OK. Then we tensor over OK with K. So OK is the Novikov ring. This guy is going to be A5 tensor A2 over K, over big K. But then we could also tensor with the residue field. And here we get F of X, comma D, little k. This is just the Kapronow-Vikerhoff. So, I mean, if you fix a graph, then this is just going to be sections of this category over the graph. And what's the theorem? The theorem is that if you have a stable object here, then it admits a representative here, which goes to a spectral network here. Okay. So that's the actual statement of the theorem. That took us years and years to figure out what the actual statement of the theorem was. So let me just finish by sketching how we're planning on approaching the proof. So how we're planning on approaching the proof is we're not actually, so the general idea is to sort of, you do some kind of minimization on the graph that's going to support an object and so on. We decided to cheat, so there's a paper by Ueda. So there's a paper by Ueda that says that this category has a B model, which is an elliptic curve divided by a Z-mod 6 action. The elliptic curve that has a Z-mod 6 action. And so we already know that you have a stability condition. So we don't need to prove that there exists a stability condition. We just use the stability condition here. And then, okay, that gives us a stability condition here. And now we just need to prove that the stable objects of a given phase have representatives. And our plan to doing that is to notice that there should be functors over here of the form like spherical functors over here, which do this same operation that I just drew here. Okay. So we say that the functors over here take objects of one phase to stable objects of one phase to stable objects of the other phase. Then we follow through what happens to we give the same definition of the functors in all these different cases. And when we get down to here, that functor is just going to do exactly what I drew in the picture. So that's the idea.